Got your first lesson on hydraulics and pneumatics. We'll get to what those are afterwards. I want to start with the kinetic molecular theory of matter, which is a very fancy title for something we understand quite well, right? And you would have studied this before. There's actually 5 states of matter, but 3 primary states of matter in our experience: solids, liquid, gas. And what these sad little pictures are supposed to represent are, and you can pause it if you want to draw the pictures, but here's the words. Particles in a solid, they vibrate, they're always moving, but they don't actually change position, they just stay close together. In a liquid, particles move around a little, and in a gas, they spread out to fill their container and they move around really quickly. Okay? So that's sort of the way we understand solids, liquids, and gases. And, we see the term kinetic molecular theory. Well, molecules are like the little particles, and kinetic means moving. Okay? I'm going to skip to the next page. So a bunch of, two other states of matter. Plasma, and you've seen this in my classroom. You've seen the little plasma ball. So this is plasma right here. And it's gas molecules, and they are so energized that the electrons have taken off. And that's what makes a plasma. So it's thought of as being hotter than gas. And then there's Bose-Einstein condensate, which I think I showed you a video. Molecules that have been cooled to just above absolute zero. I got another cute little video with Michio Kaku. I think we have to watch a commercial.
Tired of messing around with pen and paper, mass emails, and spreadsheets to get feedback? Then try survey.
I have got some fun questions here that were sent to me by some of my friends on Twitter, and so I'm gonna pop a couple of these at you. Let's see. We have Justin Gill who wrote, with the discovery of the Bose-Einstein condensate, what possible exploits can be gained by humanity through its understanding, and what effects, if any, could be seen in everyday life?
Well, everybody knows the laser. You see the lasers everywhere. They're in our grocery checkout stand. They're in our CD player. The internet is made possible by laser beams. Laser beams are everywhere. But you see, lasers are based on light. Light that vibrates in unison, called coherence. Wouldn't it be better if we could do that with atoms? Have an atomic laser. Atoms vibrating in unison. If so, that would revolutionize computation. Quantum computers, quantum teleportation, all of that depends on atoms vibrating in unison, which is the most difficult thing to achieve in the laboratory. That's where Bose-Einstein condensates come in. Einstein showed that if you cool down a substance till it's really, really cold, all the atoms vibrate in unison and you have a super atom. A super atom. You can test all the bizarre features of the quantum theory for large objects because everything is vibrating in unison. But, says Einstein, impossible, because who could cool down something near absolute zero? Well, today we do that all the time. We cool down substances near absolute zero.
We're still not to absolute zero.
Yeah, we can't reach it. That's the third law of thermodynamics.
Right.
But the Nobel Prize was given to scientists like at MIT that actually created Bose-Einstein condensates in the laboratory. What does that mean? Atomic lasers in the future. Okay? Some people even think that it may give us a shortcut to teleportation, a new way, just literally beam atoms across the room, if you can master the art of quantum coherence. For example, the CIA is interested in this because their computers will eventually run out of power. Silicon power cannot last forever. The CIA wants to crack codes. Some codes are very difficult to crack. If I have a quantum computer, I can crack the most difficult codes on the planet Earth.
Or create codes that are the most difficult to crack.
That's right. And remember that by 2020, the age of silicon will pass. Silicon Valley could become a rust belt after 2020. We could have a depression much bigger than the subprime mortgage crisis of today because silicon power cannot go on forever. Every Christmas, we assume that the previous Christmas our computers are twice as powerful. That cannot go on forever. After a while, we have to go to quantum computers. Your Pentium computer has a chip that has a layer 20 atoms across. 20 atoms across, the smallest layer in your Pentium chip. By 2020, it'll be 5 atoms across. point, electrons don't know where they are because of the uncertainty principle and will leak out, and your computer will short circuit, and that will mean a depression
That's
in
the
Silicon
end.
Valley. That is the end. So we physicists are desperately trying to negotiate that end with quantum computation, and Bose-Einstein condensates will be part of that solution.
That'll be great if we could solve that problem and continue on in our computing power.
Yeah, atomic lasers.
Definitely.
I mean, it boggles the mind to think what you can do with coherent radiation.
Yeah.
Star Trek, watch out.
Okay, so that's just a little, I showed you something on Bose-Einstein condensate before, but that's all it is. If you can get a molecule that's cold. So that means there are 5 states of matter, though we generally just concern ourselves with these, of course. Okay, keep going. There we go. So here's some terms I'd like you to copy down. Fluid, liquid, or gas. And we say a fluid is something that can be poured, but something like sand doesn't count. So, keeping in mind that something like sand does not count. When I say the term hydraulics, this is what I mean, and pneumatics, study of gases. And of course, hydraulics and pneumatics are often used to control motion or cause motion, right? And that's why we're studying them. If we use the term fluid statics, static means non-moving, so we're talking about non-moving fluids, and we'll see how we use that to do work. Pneumatic system uses gases to do work, and a hydraulic system uses liquids to do work. So you can pause to get those written down, but I'm just going to move on to the next page. Density. So we're just going over a few terms we need to know how to calculate. The first one's density. You would have done this in grade 9 science. Mass per unit volume, which means to find density, you just divide mass by volume. There's lots of different units you can use. Grams per centimeter cubed, grams per mil, kilogram per meter cubed, whatever. It depends on what you're given in the question. So looking at our example down here, we've got helium gas with a mass of 4 meters cubed and a mass of 0.712 kilogram. Determine the density. So to do the density, it's just mass divided by volume. And the units that I choose are the units given for volume on the top, volume on the bottom, and mass on the top. Okay? Again, I'm probably going too fast, so just pause. I'm going to move on. Here's a neat thing you can do with density. Because density is what we call a characteristic property, every substance has its own density. Okay, so you can, if you find the density of something, so here's an example where you come across a piece of metal, you don't know what it is. One way you could figure it out is if you knew the volume and the mass, you could find the density, and then by using the density to figure out what it is. So first we calculate the density. It's mass divided by volume. It's 19.3, okay, grams per centimeter cubed. Of course, the units are important. Okay, I give you the answer, but let me show you why that's the answer. 19.3. I'm going to skip the page here. This is just going to lead me to a table of density. So this is densities listed in grams per centimeter cubed. So if I look down, I try to find 19.3. There it is, gold. So if you did come across, or if I asked you a question like this, I would give you a table of densities. If it's in your assignment or something, you could get your own table. Just Google it, okay? But you find the density, and then that will tell you what the material is. Now, like, notice by the way, it's pure metals. So obviously, most metals, or many metals that we deal with, might not be pure, right? They might be mixtures of something. In which case, maybe the density doesn't fall on a table like this, right? But in this case, it's gold. Okay. All right, the term compressibility. So density is a property of matter. Compressibility isn't a specific property of matter, but it's not characteristic. But it is, how much something can be pressed closer together. So gases, for example, are compressible. You can squeeze them. Liquids and solids are not. And this does mean, because gases are compressible, it does limit, the ability to use gas for some types of work. You think of where you use oil as a hydraulic, right? it's because oil can't be compressed, right? So it's better to do work with using something like that if you're doing something with a lot of mass, where there could be something compressed. And this leads us into the next topic, and I'll just the questions there, and I think I'll leave you to think about the answer to that. How do snowshoes keep you from sinking in the snow? Right? What's going on there? Well, snow is obviously compressible, isn't it? Which we said that solids weren't, but it's because it's got lots of air, right? And the little snowflakes are full of air. But really, we need to get into the topic of pressure. And pressure, by definition, is force per unit area. And if you hear the term pound per square inch, right? That is pound force is a imperial way of saying newtons. It's like miles to kilometers, right? And then pounds per square inch. Square inches is area, right? We don't deal with pounds per square inch specifically. We use newtons per meter squared. That's newtons is our force and meters squared is our area. And that gives us something called a pascal. So pascal is the unit for pressure that we use. And sometimes, depending on what it is, we use kilopascals, which is just like a kilometer. Right? A kilometer to a meter is the same as a kilopascal to a pascal. So just an example. We have a ballet dancer. She bounces on one toe. The toe has that much surface area, 0.0002 meters squared. You're not going to like the numbers in this unit. They're all weird numbers. Her mass is 56 kilograms. So let's find the pressure she applies on her big toe when she's in point. Okay. So pressure is force per unit area. So to find her force, this time the force is gravity, right? That's the pressure. That's the force being pushed down on her big toe. So the force in this case is mass times 9.8. And then to find pressure, you take that force and divide it by that small little area, right? And you get 2,744,000 pascals pressure. That's the way you say Pascal. P equals the number and then Pascal. PA for pascals. Say we're looking at an elephant, though. An elephant has each foot on an elephant's 0.03 meters squared, and that's the mass. So let's find the pressure on the elephant's foot. Now I realized just now as I did this I made a mistake, because this is if all the mass. Okay, we're saying this elephant's standing on one foot, which I think in the circus sometimes they do. But if you do the question, okay, there's the force of gravity on the elephant, huge compared to the little ballet dancer, but because of the much bigger area, the actual pressure is 1.6 million pascals, or 1,633 kilopascals, less pressure on that elephant's foot than on a ballet dancer's toe. Now this is an elephant on one foot. So if we actually multiplied that to find out, for like if we were to divide it by 4, we could split that up between 4 feet. So that's about 400 kilopascals, really, on each foot if he's on all 4 feet, compared to the little ballet dancer on her big toe. Anyways, that's calculating pressure. Another little food for thought question. Using the idea of pressure and being force per unit area, how would having smaller boxing gloves affect the sport of boxing? Right? If instead of using a big cushiony, big huge glove, you had tiny. And I guess maybe this question has been answered with what's it called? Is it mixed martial? No, what's it called? Ultimate fighting or whatever they do. We know a little bit more about how damaging that can be. Okay, so here's just a little summary that you can put down. I don't know, I put down these triangles. I don't know if you use these or not. They sometimes help with the calculations because the idea is that if you're looking for, because density is mass over volume, say you're looking for mass, well then you would cover up mass on this, you'd cover this up, and then mass equals those two multiplied together. If you're looking for volume, you'd cover up the V, and then volume is mass divided by D. That sort of thing. So those triangles can help you with these calculations, but these are the rearranged formulas, whichever you want to put on your formula sheet, whatever works for you. But there's the basic formula for density and pressure. Those are what they mean. There's the rearranged forms, and there's the units. And then sometimes pressure is if the force happens to be gravity, then pressure is mg over A. But that's only specific if the force is gravity. Okay? And I guess it's important to know you have to use kilograms and meters squared. With density, you don't have to. You can use whatever. Whatever's given, you can use. But with pressure, you have to use kilograms. Okay, so that's it for the first lesson on this unit. I'm going to stop there.